All right. So in today's session, we want to look at chemical equations. So far we've looked at the three states of matter, then went on to look at atomic structure. From atomic structure, we started looking at bonding. We looked at ionic bonding, and we touched on the periodic table, and we came back to covalent bonding. So we're at the point where we want to get into writing chemical equations, right? Now, in order to write chemical equations, we need to apply some of the knowledge that we learned in ionic bonding as well as covalent bonding. Because apart from writing equations, we need to be able to write formulae, right? So we need to understand, we had to go through bonding so we understand how molecules, how atoms or elements bond together ionically based on charges and the exchange or swapping of charges, so we can write the ionic formula. And we had to understand covalent bonding as well in terms of monatomic, diatomic, triatomic covalent bonds or molecules. Right, so let's get into it. So basically, a chemical equation is an equation that depicts how a chemical reaction occurs. We use symbols, right, to determine the state of matter each of the reactants are in, as well as the products. And we use formulas to represent the reactants and products. This is why it was important for us to look at things like the periodic table, to learn our the element symbols, as well as the ionic bonding to the charges, etc. Now, when we write in our chemical equation similar to maths, we have a right and a left-hand side, a left-hand side and a right-hand side of the equation. Instead of a equal sign, we use an arrow. So the reactants are separated by plus signs, and they appear on the left-hand side of the equation. The products are also separated by plus signs if there are multiple products, and they're shown on the right-hand side of the equation. The arrow replaces the equal sign that we usually use in maths, and that separates the reactants from the products. It also may include any conditions that is necessary for the reactions to occur, right? This could be in terms of temperature or in a particular type of pressure or a catalyst to speed up the reaction, right? Now, we want to look at writing balanced equation. Now, there are a couple of steps that we usually take in order to write a balanced equation, right? So when we have to write an equation, it has to balance. What do I mean by the equation needs a balance, right? It means that the total number of atoms of each element on either side of the arrow has to be the same. Now, very often, for CSEC purposes, we may have a reaction given in words. For example, we have here magnesium oxide plus, or it's being reacted with hydrochloric acid. The reactants is going to be magnesium chloride and water, right? We look at different type of reactions a bit later on. Our focus is mainly on writing the equation and balancing the equation. Now we move from the words to the chemical formula, right? So magnesium oxide, which is ionic bond because we have magnesium and oxygen bonding together. Remember, when we have to write the formula for that, we are looking at the charges, which is really based on the outer shell electrons. Magnesium is in group 2 with 2 electrons on the outer shell, right? And oxygen is in group 6, right? With 6 electrons on the outer shell. So magnesium is exchanging 2 electrons with oxygen. Oxygen is accepting those 2 electrons. We only need 1 magnesium atom and 1 oxygen atom. So that's why the formula there is MgO, right? Hydrogen chloride, same thing. Chlorine has 7 electrons on the outer shell. Hydrogen has 1. Hydrogen is donating its electron to chlorine, again another ionic bond. Now, when these two react, what we have been formed is something called a salt, right? Magnesium chloride is a type of salt. We look at these type of reactions between oxides and acids in our next couple of lessons. Now, when that happens though, notice that we have MgCl2, because if you remember from our exercises we did with ionic bonding, magnesium has 2 electrons to donate. Chlorine could only accept 1. So in order for those two to bond together, we need 2 chlorine atoms to accept the 2 electrons coming from magnesium. This is why we have a MgCl2, right? And then with water, we have the same thing happening there, right? Oxygen needs 2 more electrons to complete its outer shell. So 2 hydrogen atoms bond together covalently. The oxygen atom in order to give us H2, right? So those are the molecular formulas for magnesium chloride and water. So we looked at the words, we then looked at the formula. We need to show the physical state of the reactants and the products, and we place what we call state symbols after each formula. So the state symbols that we usually use is S for solids, L for liquids, G for gases, and AQ for aqueous solution, right? Now, the magnesium oxide is a solid in this reaction. The hydrogen chloride is aqueous. Anything that is not water is referred to as aqueous solution, right? It's a solution, right? It's made up of a solvent and a solute, right? Water being added to something. So when we react magnesium oxide with hydrogen chloride, we actually get a soluble salt for magnesium chloride. So it's dissolved inside of a liquid solution. Well, I shouldn't use the word liquid solution, but I should say it's dissolved inside of the solution. Inside of there as well is water. Water is our true liquid, right? So alcohols. After we include our state symbols, we need to balance this equation, right? You see, the same number of atoms that we started with should be the same number of atoms that we end with. Now, currently, if we do a simple tally of the atoms that we have on our left and right hand side of the equation, what we will see happening is that there's a slight difference, right? If we look at the reactants, I've listed the number of atoms. You have one magnesium atom. I can tell that because there are no subscripts. Subscripts are the little numbers that we see written at the bottom. So, for example, with the magnesium chloride, there's a 2 written at the bottom as a subscript next to the chlorine atom. That tells me that there are 2 chlorine atoms. So if you compare the number of chlorine atoms on the left-hand side where the reactants are, and that on the right-hand side where our products are, there's a bit of a difference there. There's one chlorine atom on the left-hand side, but 2 chlorine atoms on the right-hand side, right? So it means we have to balance these equations. This equation is not balanced, right? So how do we go about doing that? Well, we can see as well too that the hydrogen atom, there's 1 on the left and there's 2 on the right. So what we need to do is we would place numbers, kind of like a factor or scalar, in front of these atoms in order to balance them, right? Let's take a look at how that would look. To balance the equation, we place simple whole numbers, like coefficients, like what we would use in algebra, in front of the formula so we could alter the proportions of reactants and products, right? We're not changing the formula. If we put them in as a subscript, that means we are changing the formula, but we are not doing that. We are placing them as coefficients in front of them. That means that we'll have 2 HCl molecules there, right? That's going to be able to provide the balancing of the equation, right? So that those 2 hydrogen atoms and the 2 chlorine atoms. Because think about it. If we wrote it initially and this had no 2 there and there's just 1 H and 1 Cl, how is it then that another chlorine atom is coming here to bond with this magnesium? And where is the other hydrogen coming from? It means that on the simplest scale, for magnesium oxide to react with hydrogen chloride, you actually need 2 hydrogen chloride molecules in there. So that when you react, you will have 2 chlorine molecules that could bond with magnesium, and you could have 2 hydrogen atoms that could bond with oxygen to form water, right? This is what we mean by balancing the equation. Does that make sense to you? You understand that? Right. So in order to write balanced equations, as I mentioned earlier, we have to be able to write correct formulas for compounds. If we can't do that, then we're going to have issues in terms of balancing equations, right? Because incorrect formulas lead to incorrect equations and incorrect balancing as well. So we're going to turn our focus a bit to the writing of formulas. So we're going to recap some of the things that we learned with ionic bonding and covalent bonding. Now, it is very important for us to not only know our first 20 elements, which was an exercise that I gave you guys to write out at the beginning, where you list your 20 elements, you list the atomic number, you list your mass number, you list the number of protons, electrons, electronic configuration, right? That ties in somewhat into this table that we have here, because we have a number of elements that are what we refer to as monovalent. meaning that the charge that they will have when they lose an electron, right, will be a positive charge. Now, there are some other molecules included in here that we need to know as well. Hydrogen, lithium, sodium, potassium, copper 1, and silver, all in their elemental state. Ammonium, is a molecule. It's made up of nitrogen and hydrogen bonded together. But this molecule gives up a lone electron and also has a positive charge, right? So we need to know that so that when we are writing formula, let's say for ammonium chloride, we will know what charge the ammonium molecule or ion, so to speak, would have. We have divalent molecules as well, or divalent ions. This means that they all have charges of +2 or 2+. And then we have trivalent, which means they have charges of 3+. Now, these are all cations on top of here. And below, we have the anions. So it's important for us to learn these so that when we have to write our ionic compound, the formula for the ionic compound, we can simply cross our charges as I've demonstrated before. So we will know how to write them. So for example, if I want to write the formula for aluminum chloride, the formula for aluminum chloride will actually be AlCl3, with the 3 being a subscript. And why is that? Because chlorine is monovalent. It can accept 1 electron. But aluminum is trivalent. It has 3 electrons that it needs to offer or give away. So we need 3 chlorine atoms in order to accept these 3 aluminum, these 3 electrons from the aluminum. So what we use is a kind of crisscross method where we look at the charges and we cross the charges. So for example, if I want to do aluminum oxide, what we will get really is Al2O3, right? Because you're going to need 2 aluminum atoms to provide 6 electrons and 2 oxide in order to accommodate 3 oxides, in order to accommodate 6 electrons from aluminum. You okay with that? Does that make sense to you? Right. The same thing happens if you want to do a trivalent and a divalent. We will crisscross the charges, and that helps us to easily write our formula. So you can practice swapping charges to write formulas, right? So these are this is a table that you need to learn all of these, right? Now for covalent compounds, we have to pay attention to the valencies. When we talk about the valencies, we're talking about the number of electrons in the outer shell. And you'll see here again why that table with writing our electronic configuration was important. Because we need to think about the electrons on the outer shell, right? These are our valence electrons. So if I have 2 atoms, I'm just randomly calling 2 atoms, T and W, and I say that my proton number, atomic number is 6 and 9 for each of them. That means that my electronic configuration will be 2,4, which is the same electronic configuration of carbon, and 2,7, right? Which would probably be fluorine is 17. So this is probably lithium. Sorry, maybe fluorine. Fluorine is 9. I'll have more textbook here. But anyway, what we want to do is when we write in our the formula for our covalent compound, we take the valence electrons and we swap them in order to create the simplest whole number ratio of the number of atoms that will combine. So if I am bonding T and W, what will happen is I will get TW4, right? Because 4 of these are going to be shared with, we need 4 W's, right, in order to complete the outer shell of T, right? So this is like if you think of something like carbon and hydrogen, CH4, right? Similar. Now remember, covalent bonds can be monovalent, divalent, trivalent, right? Here are some prefixes as well, because when doing our covalent bonds, sometimes you may find compounds that would require 4 atoms. We use tetra for that, penta for 5, hexa for 6, hepta for 7, octa for 8, non for 9, and deca for 10. So these are some important prefixes that you need to know when you're naming formulas for molecular compounds. Molecular compounds will be covalent compounds, right? So the compound formula for covalent compounds usually is made up of our different elements. So the elements farthest to the left, right, or the bottom in the periodic table would always come on that left-hand side, right? We will see the number of elements that we need. So here we actually need 2 nitrogen and 3 oxygen. And if you think about it, if you look at the valencies for these, right, the number of electrons on the outer shell of the nitrogen will be 3. The number of valence electrons that is will be 3, and the valence electrons for oxygen will be 2. Nitrogen actually has 5 electrons on the outer shell, so it needs another 3 in order to complete its outer shell, right? Oxygen has 6, so it needs another 2. So when we're talking about the valencies, we're talking about the number of electrons to complete that outer shell. So that's what we swap in between the two of them in order to figure out the compound formula. If I just go back to this, right? The number of electrons needed by an atom to achieve a stable octet electron arrangement. So this needs another 4, this needs 1. These are the values that we are swapping. We're not swapping the 4 and the 7. All right, and that's how we come up with the compound formula. Now, in terms of the compound name, right, we have the prefix. The prefix is based on the number of atoms we need here. So remember this last chart here, di is what we will use for 2, like a pair of dice, right? So we have di nitrogen, and then we go with the other prefix, right, which is 3. So that's tri. And then what we have is the root word or the root name, which is oxygen, and we will always add a "ide." So we have dinitrogen trioxide, right? So the prefix denotes the number of atoms. Understanding this is important because sometimes if we are given the compound name and we have to write the compound formula, right, we could use the name in order to figure out what the formula would be. Does that make sense to you? Here are some examples. So we just saw dinitrogen trioxide. This one is going to be chlorine, right? So we name it the one from the one in front is going to be chlorine, and we'll have dioxide. This one is going to be boron trifluoride. You see how they keep adding the "ide" at the end of it. This one here is tetraarsenic. Arsenic is another compound. Deca. We use deca for 10, or decoxide, right? Carbon monoxide, you have 1 O here, right? Diphosphorus pentoxide and nitrogen dioxide, right? So these are all examples of some compounds and the way in which you will name them, right? So I want you to take a little time. We have a little activity for you to complete now, right? So I said I'll write these formulas, the first 2 for you, right? So ammonia, the formula for ammonia is actually NH3. So I'd like you to learn that one. And then for ethene, we have C2H6. Right, so learn that one from me as well. What did you get for phosphorus pentachloride? What you got for that one? What you wrote as your formula? Got one? You was able to figure that out? Earlier? Right, PCl5, good. And nitrogen dioxide? And 2, good. For diphosphorus trioxide? I got for that one. P2O3, very good. fluoride, trifluoride, fluorine trifluoride, right, sorry, I missed that one. Cl, F, good. Sulfur, hexafluoride, right? Six, hex is 6, good. Arsenic trioxide, good. Sulfur trioxide, SO3. And last one, nitrous oxide. This one was a little different, N2. Very good. Right? So these are some common covalent compounds. So it's good to know the formulas for these. All right. As you do more questions, eventually you'll see new formulas. And when you get formulas that you're unaware of, like I said, you should keep probably a couple of pages to the back of your book for logging some of these things, for like your electronic configuration, tables with your monovalent, divalent, and trivalent ions and cations. Right? Compound names, right? Irregular and common ones. States in terms of whether they're solid, liquid, gases, aqueous, especially uncommon ones. What again? When we do acids, bases, and salts, in general reactions to those, right? So it's like kind of like you have a, like in math, you'll have a formula sheet, right? For chemistry, you want to kind of build a repository of general information, general knowledge that you should know. All right, so we're going back to our slides. There. So just now we looked at the names and we wrote the formulas. This exercise, you're going to look at the formulas and try to write the names. All right? Think you could handle that for me? All right, so let's take a look at this. We want to write the name of the covalent compounds. First one, we have CO. What you got for this one? Good. Carbon monoxide. And then we have CF4. Good, very good. Carbon tetrafluoride. And then we have BCl3. Good. Boron trifluoride. And then this one, C2H2OH. Might have been a little challenge. Ethanol, very good. H2O2. Very good. SO3. Good. N2O5. Very good. BRF5. No, BR will be what? Bromine. Bromine. Yeah. pent. This one, GES2. I didn't. GE is not one of the elements that we need to know on our syllabus. But did you look it up? What you got? Germanium. Yeah, disulfide. That's correct. And last one, HCl. Excellent. Very good. All right. So that was some good practice there. Let's go back to our slides. Right. So we looked at covalent formulae compounds, naming covalent compounds. Now we're going back to balancing our equations. Right? So we have some more examples to look at. Let's look at this one. We have sodium reacting with water. Now we said the first step we would usually have in words, right? So we have sodium plus water to give us sodium hydroxide and hydrogen. Second step is you want to write the symbols to these. So sodium is Na, water H2, sodium hydroxide is going to be NaOH. Again, this is a ionic compound, so we have a positive Na and a minus a negative OH. So we get a formula NaOH. Hydrogen in its elemental form is H2, and that's a gas. So step 3, we put in state symbols. When we have something listed in its elemental form, right? Some of them, like the metals, they will all be solids, right? Some of the non-metals as well, and then you have the gases, right? They some of these exist as gases. You get closer to the right-hand side of the periodic table, a lot of these exist as gases in elemental form. So writing our state symbols, the next thing that we need to do is check to make sure that after we write in the state symbols, step 4, we have the same number of reactants and products. So on the left-hand side, the number of reactants we have, we check each element. We have 1 sodium, 2 hydrogen, and 1 oxygen. And then we check on the product side, 1 sodium, 1 oxygen, and we have 3 hydrogen. So we have 1 more hydrogen than needed on the reactant side. Now, step 5, because H doesn't balance, sometimes what we need to do is we might need to find what I usually would call the LCM of two of the things. Let's look at it. If we place a 2, because we need 2 hydrogen on one side, in front of the H2, and then we place a 2 in front of the NaOH, look at what happens, right? We're going to get 2 oxygen instead of 1. We're going to get 4 hydrogen instead of 2. On the product side now, if you place a 2 in front of the sodium hydroxide, we're going to end up with 2 sodiums, 2 oxygens, and 4 hydrogens. Now we have the oxygens and hydrogens being equal. But now the sodium is not balanced. So we need to go back again on the reactant side and we put a 2 in front of the sodium. Right? So somewhat of a kind of puzzle sometimes. You might start with one thing and then when you balance those 2, you realize another one need balancing. Right? So we put a 2 in front of the sodium here, and now that balances the equation. Yeah? Now here's some tips when you're balancing equations. When you're balancing equations, for elements in a free state, you use the molecular formula, right? A lot of these might be diatomic, like we saw hydrogen, nitrogen, oxygen, chlorine, bromine, and iodine. All of these are diatomic elements in a free state. You always begin by balancing elements in the product immediately after the arrow. So that's the first place you should try to start to balance, right? Like in our previous example, you notice they went to the sodium hydroxide molecule. That's a good starting point, right? Then you will balance any polyatomic ion that remains unchanged from one side to the other as a unit. When we talk about a polyatomic ion, we're talking about things like the sulfur, this is a sulfate ion actually, SO4 2 minus. If it appears on both sides, you treat that as a single unit. So you're not going to say, well, if I put a 2 in front of SO4 2 minus, that you have 2 hydrogen and 8 oxygen. You treat that entire thing as an entire unit. You're not splitting it up. You understand what I'm saying there, right? If a compound contains hydrogen or oxygen, balance the hydrogen second to last and oxygen last. Right? Leave elements in their free states until the very end for balancing. So magnesium, copper, Cl2, H2O2. Notice that we left the sodium last for balancing. And always ensure that the coefficients are in the lowest possible ratio. Right? So you want to reduce it, like how you reduce fracture. Right? Here's another example. We have Al, aluminum, plus this is sulfuric acid to give aluminum sulfate and hydrogen gas. Right? We want to balance this equation. We start with the product immediately after the arrow. Right? So Al does not balance. We could see clearly here Al and Al2 is not balancing. So we want to start by looking at the one right after the arrow. Right? So you balance this by placing a 2 in front of the Al on the other side, so that now these two could balance. Right? So we'll have 2 Als, right? We still have, after we do that, we could see that we have the hydrogens, right? 2 on either side, right? And we have the sulfates. We have one, remember, so let's treat this as a single unit. We have one sulfate ion, right, on the polyatomic ion on our reactant side, but 3 on this side. So that's the next thing that we want to look at. So we're going to put a 3, right, in front of here so that we could balance the sulfates. But in doing that, which we would achieve, because we will now have 3 sulfates here and 3 sulfates here, we have the 2 aluminums here and we have the 2 aluminums here. By placing this coefficient here, we make our H into 6. And that's why we leave these for last. Now the H doesn't balance. So the last thing to do now is place a 3 in front of the H2 on this side, and then we'll be balanced. So you see how it works? So you always start by looking at the reactant right after the arrow. And you compare it with your reactants. I meant to say the product right after the arrow. And you compare it with the reactants on the other side, and you start balancing the equation from there. Right? Now state symbols of ionic compounds. Now, if a compound is soluble, it would be usually given a state symbol of AQ, meaning aqueous. If it is insoluble, then we will give that state symbol a S. Now, most ionic compounds are soluble in water. Remember when we learned about the water molecule with that polarity, the electronegativity of the oxygen creates a dipolar sort of charge. So it helps when the ionic compound is dissolved in water to kind of separate them apart, right? This is why they're soluble. But there are some that are insoluble. So it's very important for us to learn the rules that determine the solubility of ionic compounds. This is another table you need to add to your little index to the back of your book, right? So compounds that are from potassium, sodium, and ammonium, they are soluble in water. There are no exceptions to that. Nitrates, all nitrates, wherever they come from, are soluble in water. Fluorides are soluble with the exception of silver and lead chloride. Those are both insoluble, right? Lead chloride is partially soluble in hot water. Sulfates are soluble with the exception of lead-2 sulfate and barium sulfate, and calcium sulfate is slightly soluble. The ethanoates, they are soluble, and hydrogen carbonates are also soluble. There are no exceptions to this, right? So this is another table that you have to learn. Common ionic compounds which are insoluble in water, right? So we have solubility in water, carbonates, they're insoluble, phosphates insoluble, hydroxides insoluble, metal oxides insoluble. Of course, they're the exceptions. The exceptions here are those more reactive carbonates like potassium and sodium, right? You'd see potassium and sodium repeating itself, and that's because of where they are in their respective groups. Right, same thing for the metal oxides. Ammonium carbonate, ammonium phosphate, and ammonium hydroxide are also soluble, and calcium hydroxide is slightly soluble, right? So these two tables are two tables that you need to add to your little index to the back of your book as something for you to learn. Yeah? So you have some practice. I want you to practice balancing each of these equations using the same rules that we spoke about before. And then the other exercise, you're going to state which of the following ionic compounds is soluble or insoluble in water. All right, you think you could handle that for me? All right, so let's look at these equations. Starting with A, we have Br2, right? So they were kind enough to include our symbols and our state symbols, and all we required to do is balance these. Right, so we said that we need to check the amount of atoms we have on either side of the sign. So we have one Br, we have one K, we have one I. On this side we have one K, we have one Br, and we have two I's. Right, we should always start by looking at the one closest to the arrow. Right, so if we put a 2 in front of here, right, we'll be able to balance this, but then that makes this a 2, right? So we could come here and we could put a 2 in front of this. That's going to make this 2, and that's going to make this 2. And now we could check to see if we balance, right? So I usually use a little tick, right? So that with that, this with this, and this with this. Okay? Got that for the first one? Yeah? Okay, nice. Yeah. Next we have Fe plus Cl2. Equal to FeCl3. Right, so again, we want to list all of the atoms on both sides of the equation. Right. Now, when we have this happening, we have a 2 and a 3 here. We swap it. We're actually looking for our LCM. So if I do by 2 here, that's going to make this 2. And that's going to make this 6. And then to get 6 here, I'll just multiply by 3. This will give me 6. And then to deal with the Fe, we'll just put a 2 in front of here. That'll make it 2. We check 2 Fe's, yes. 6 Cl's, yes. But that for the second one. Very good. C, we have aluminum and sulfuric acid. Aqueous. Right. So again, we list one Al here, two H's. One, remember to use this as our entire unit. We have two Al's. We have two H's on the side, and we have three and so forth. Right. So we start from here. So on this side, we need two Al's here. right? Then we look, we have 3 SO4s and we have 1 here. So I need a 3 in front of this. That'll give me a 3 to balance with this. But now that makes this 6. And to get this to become 6, I need to put a 3 in front of it to make it 6. So how we balance? I have 2 ALs, yes. I have 6 H's, yes. And I have 3 SO4s. Yeah? Got that for the second one, for the third one, sorry.
Yes, sir.
Very good. And oxygen, carbon dioxide, and water. Good. So we go here, 2 carbons, 4 H's, 2 A's, 1 carbon, 2 H's, and we have 1, 2, 3 O's. So we could start here. So we definitely need a 2 in front of this so that we can get the 2 carbons to be the same. But then when we do that, we end up with 4, 5 O's. All right. We look on this side. We need 4 H's. So if I put a 2 in front of here, right, you're gonna get 4 H's. And now we have 4 O's and 2 O's, 6 O's in all. Draw a line through this. This is fine. This is fine. And we need 6 O's here, so we put a 3 in front of this to make it 6 O's. Yeah? You okay with that one? Yeah? Then move on, right?
Yes, sir.
Okay, sodium hydroxide and ammonia sulfate. Yeah, gas and water. Right, so if we list this off, we have 1 sodium, 1 oxygen. Check this as 1 OH molecule. Then we have 2 NH4s, 1 SO4. On this side, you have 2 NAs, 1 SO4. Two N's, 1 SO4, 8 H's. 2 NAs, 1 SO4, 1 N, 3 H's, 2 H's. So if we start here, we need a 2 in front of this Na. But then that makes this 2 and this 2 as well. Right? Our SO4 is good for now. We look at this next. We only have 1 N, we need 2 N. So if I put a 2 here, and makes this 2, right? But then it makes this 6. Right, so let's see what we have going on so far. We okay with the NAs? We okay with this? We okay with this? Right? Our oxygens, we have 2 oxygens here now, and we need to have 1 here. So I need a 2 in front of this. That's gonna make this 2, and that's gonna make this 4. So my oxygens will be fine. And let's check the each shift now. We have 2 and 8, that's 10. 6 and 4, that's 10. Yeah? So that's our balance equation. You got that for this one?
Yes, sir.
Very good. Right? So taking that approach works out fine in terms of balancing equation. Let's just do the other one. So silver nitrate, you're going to tell me. Is silver nitrate soluble or insoluble?
Soluble.
Soluble. Very good. Zinc hydroxide.
Soluble.
Soluble. That was one of the exceptions. Let's double check. Hydroxide. Soluble. Okay, you mean soluble ones are potassium, sodium, and ammonium. Very good. Right. Lead chloride.
Insoluble.
Good. Calcium carbonate.
Soluble.
Soluble. Good. Potassium phosphate.
Insoluble.
Insoluble. Good. Aluminum sulfate.
Insoluble.
Insoluble. Copper 2 oxide.
Insoluble.
Insoluble. Good. Right. The metal oxides. Metal oxides are soluble or insoluble? Copper 2.
Soluble.
Soluble. Correct. Right. The insoluble ones will be the potassium, sodium, and ammonium. So this one is soluble. And your sodium ethanoate.
That one will be soluble.
Soluble. Very good. All ethanoates are soluble, there are no exceptions. All right. So you okay with this?
Yes, sir.
All right. So remember, just to wrap up, the table with your different monovalent, divalent, trivalent ions. That's something I want to pull out and put to the back of your book so you learn those. The table with your solubility for different compounds. That's another thing that I need to learn. And just to recap what we did with the balancing of the equations, you always want to start with the product that's right after the arrow. Start from balancing there first, and then you work your way outwards to the rest of the equation. Also, before you get to doing that, you want to list the number of atoms. You don't separate those like sulfate. In other instances where you will know when to separate it. If it changes on either side, so for example, you saw in the last one we did with ammonium becoming ammonia gas. It's not the same on either side. So we had to separate the nitrogen and the hydrogen into individual atoms so that we could balance. Sulfate, SO4, remain the same on both sides of the equation. So we treat it as a single unit instead of breaking it up. Understood? Yeah?
Yes, sir.
All right. So that brings us to the end of our lesson for today. I have the link to send for the last session we did, which was on covalent bonding, and that should be ready to view in YouTube. So you get that inside of the chat, the link to the video. All right. Any questions before we go? No? All right. You did a good job answering these questions. So I think you have a good handle on it. All right. So we wrap up with that for today, and I'll see you again next week, Saturday. All right. Same time, same place. Take care. Have a good weekend.
So,
All right. Bye bye.
Yes. Yes. Well, yes. Well, yes. Yes. There are 3 reasons to learn math as an adult. 1, helps every career. A stolen Lamborghini fleeing officers. Have to stay a season ahead of yourselves. So let's say you got a 10-year-old or 11-year-old, okay? He's not handling guns. He's probably not handling a lot of knives. He's probably not driving a lot of heavy equipment. He's not driving your car yet. But they get it going. Because you want to grab your teacher for 10-year-old son. You want to grab the tractor? Yeah. Okay. But you're going to drive a tractor. I need to be able to trust you. Okay. So that means that when we ask you to clean your room, and you say you did it, but you didn't do it, I can't trust you. You connect doing fun things to real things, so they can connect cleaning their room to driving the tractor. Because you can't be trustworthy in one area and not in another. That's called lack of integrity. And so you're gonna teach them how to.
I played around with it and some got like a million views. I didn't even do anything. I just put the link in.
Obviously, it's one of the most practical AI tools out there. Are you over 40 and want to master AI tools? I got you. System. How did this? Work out every day until September 1st. Do not buy a card. Bodyweight workouts to do before bed. Don't give up. Dark times teach bodyweight workouts to do before bed. Right here, we got squat down, kick outs. 1 minute. Let's go. Next workout, we got in and out squats. These burn. So make sure you keep going.
Here we got standing body crunches. Let's work through it 1 minute. Last but not least, sitting kick outs. Let's go. Work them out, baby. A lot. That's why you can't regret what you went through, but rather be thankful. Be over because I'm black. It's 2 o'clock in the morning. Everyone is black.
That's it.
Oh, yeah, change. To the
Number one.